Yeah, thanks for the heads up about move in. I did not realize that. And the whole spring break thing is just weird anyway. I probably shouldn't record that and put that on YouTube, but it is. Okay. All right. So I want to remind ourselves, we started doing an example the other day. We're going to walk through the same process. We got 6 steps, and we've got a whole MATLAB process that we're going to walk through to try to do it today. So our last example that I'm going to do here, I did mention that I was going to post some additional examples, and I still plan to post some additional example videos that you guys can see. Probably another 2 examples in addition to this one, and that should be plenty to be able to kind of work through these types of problems. Okay. All right. Here is the circuit we're going to tackle. We started to do this the other day, but I want to wrap this one up. And in particular, what we wanted to do in this guy is I want to find the capacitor voltage V of t for t greater than or equal to 0. Okay. That's going to be our goal. And I somehow made it disappear. There we go. All right. And we're going to go through the code here as well today. All right. That's going to be the basic approach. Okay. So V of t for t greater than or equal to 0. So we got to go through my steps. What's the first step? What's
Write
step
the
1?
differential equation.
Yeah, write the differential equation. Now this one, all right, is a really good example because in this particular one, this is one where it's not just a parallel RLC or a series RLC. There's some steps to it. Okay. So in particular, I write the differential equation, but what's the condition? I'm doing it for what condition?
You mean like d squared V of c?
Well, I mean, I get in particular, what what time condition?
For t is greater than 0.
T greater than 0. Yeah, and specifically, I'm worried about the transient period, right? So I'm not making any replacements for my L's and C's. The L's and C's are doing their thing during this time period. Okay. All right. So before I get going too deeply into this, what are the key relationships? I'm going to define a couple of things here because I want to do this sort of symbolically again. I have R1 is this 4 ohm, and I have R2 is this 2 ohm resistor. I'm going to call them that. And I've made some definitions here, V4, VL, V2, IC. All right, so in terms of the variables I've given here, what's the relationship I have for the inductor there? What's the voltage current relationship for the inductor?
IC equals C dVc dt.
For the inductor.
Is it VL equals
L di.
Yeah. VL is L dIL by dt. All right, and the other one, whoever had said that was, so IC is C d voltage capacitor, right, by dt. In this case, it's defined as V, right? So I have those relationships. At this point, there's nothing special about the capacitor voltage and the inductor voltage. There's no special things here like there would be in a series or a parallel circuit. I just have those 2 relationships. Okay. All right. So let's draw the circuit here. So I got 12, and I'm going to draw it specifically for the situation where the switch is closed. Okay. So I have that. All right. So how do I approach this problem? Where do I begin?
Start by doing a KVL on the left side.
Start by doing a KVL. Yeah. So, so how would I do that? So again, what I do is I make sure I've got labeled properly everything here. All right. And I have I going this way. Okay. So 0 equals, when I do my KVL equation, 0 equals minus 12, right? I go plus to minus on the 12-volt source. Then what do I do with the resistor R1?
Voltage of resistor 1.
Which is what?
Oh, is
V4 over R1.
Yeah, so V4 over R, well, it would be V4, right?
It'd be
Well,
I times R1.
Because it's
Yeah,
not-
so let's just do it that way. So it's V4 as I've labeled it, plus VL, plus what?
V2.
Plus V2. What does V2 equal to?
VC.
Yeah, the capacitor voltage, which is written there as just straight up V. Okay.
Can I ask a quick question, Dr. Cox? In the homework, one of the troubles I had, because like once you have the differential equation, it's easy to get the ball rolling. Like that's the hardest part, I think, about this whole process. But how do there's been homework problems where we do either KVL or KCL. And even though it's asking for like capacitor voltage, how would you make that distinction? Like, hey, it'd be easier to tackle this problem with KCL, or it'd be easier to tackle this problem with KVL.
Well, I mean, I got to just look at I mean, it's one of those things I just got to look at the problem and kind of look at the tools that I know and figure out which one is the right one to use.
Because I would have used.
There's not necessarily, so there's not necessarily a straight up rule of thumb here. It's just that I have to combine the tools to get to that answer. So I think I know what you're about to say, which is you would have used KCL. Is that what you're about to say?
Because I'm seeing I goes in,
And-
you got I2 and IC,
Yeah.
so it seems.
And
simple.
we're going to use them both.
Okay.
All right. So this is a case where, you know, I need to get to an equation that's got a second order term for V, right? And I'm not going to be able to do that in this case with just KVL. So let's put some substitutions and keep going with this and address your question. So 12 equals V4 plus VL plus V. So V4, which is the voltage across this 4 ohm resistor, I'm going to write that as I times R1. And VL, I'm going to write as L di by dt. And V, I'm just going to write like as V, like so, because V is what I want, right? I'm trying to find for the capacitor voltage V. All right, now, that's not a differential equation that I can use yet, right? What do I need to do? I need to, if I want to get to a differential equation that's just in terms of V, I need to get rid of I, right, in this equation.
So you just divide.
No, you would do a KCL and then plug in.
Yep.
Well, we'll get to that step.
Yep, we'll do a KCL. That's our next step here. I, which is the current in the inductor, equals what plus what?
I2 plus IC.
Yep, I2 plus IC. Right? I2 plus IC. So you look at that top figure here. I2 is the current in that R2, and IC is the current in the capacitor. Okay. So now that I have, you know, that value there, right? What do I know about IC? And what do I know about I2? How can I relate I2 and IC to things that have to do with the capacitor?
IC equals C dV dt, and I choose VC V over R2.
Yep. So V over R2 is, so the voltage across that capacitor divided by R2 is the current in that resistor plus C dV dt, like that. Now, what do I need to do now to try to get to one differential equation?
You could take that V2 or that V over R2 and you just plug that in for your I values in the KVL equation.
Yeah. So my I is this, and I'm going to plug that into my KVL equation. Right. So I'm going to have 12 equals, we had I R1 plus plus L di by dt plus V. So I'm gonna put in there what I had on the previous slide for I. So I'm gonna have R1 times V over R2 plus C dV dt plus L d by dt of that same expression, V over R2 plus C dV dt plus V. All right. So this guy right here is I, And this guy right here is I. Okay. Then what I have to do is just sort of simplify that now. So I have R1, R2 times V plus I have R1C times dV dt plus, okay, what do I do with this middle term? I think this is where everybody gets all confused.
You just multiply out the ddt, so it would be like 1 over R2 dV dt.
Yeah, L over R2 times dV dt plus, I get a second derivative, right? LC.
And dV squared over dt squared.
Yeah, plus V. All right. So by the time,
right?
So now I got that's a second order differential equation right there, isn't it?
Yep.
All right. So basically, if I group everything here, I'm going to have 12 over LC equals d squared V by dt squared plus R1C plus L over R2 times dV by dt plus V over LC.
You forgot divided by LC.
And I didn't divide by LC in this guy. So this guy's going to be R1 over L and 1 over R2C. Like that. Okay. That's what that simplifies down to.
Yep.
Okay.
What about that R1 over R2V is added to the...
Oh, sorry, yes. And 1 over LC times 1. This should be plus 1 over R1 over R2, like that. Right. That's all the terms in that guy. All right. So what I do at the end of this step is I'm saying, well, this is I put this in my standard form. This is my little c. This is my A term. And this is my B term in terms of that differential equation. And I should say the B term is actually got the 1 over LC in it as well. Okay. You guys follow that?
Yep.
All right. So now what I do is I go to my Matlab code here and let's see what I've done. So what I've done is I've defined for myself R1 is 4, R2 is 2, C is 0.5, L is 1, right? And those are all values that are consistent with what so I got 0.5 farads, L is 1, right? So it's all consistent with that guy, right? And what I've done is I've put in the values there for A, B, and C. Okay, so now I've got that. All right, that's really kind of the completion of step 1, right? Step 2 is now I got to figure out what. Step 2 says solve the differential equation to find the general form of the solution. Okay. How many forms did we consider and what are they?
3 forms.
Yep, 3 forms.
Under damped, over damped, critically damped.
You got it. Over, under, critically. Okay. So this is my step 2 here. Now I would expect you to go back and look at this now and go back to the sort of that summary. But now that I have those values there, so I have, numbers for A, B, and C. So those yield for me alpha values. Alpha, if I go back to my formulas, is that. And then I have my B value. So omega naught is equal to the square root of B. All right. What do I do with those values?
Once you get them, you compare them to each other to see if they're like if lambda's less than or greater than W naught or equal to it.
Yeah, right. So you can look at the values of alpha and omega naught. And again, if you're more comfortable from differential equations, you're going to have this as your characteristic equation. You could get the roots of that straight away and figure out what this guy is, right? So if I look at alpha and omega naught in this particular case, and I run the numbers, let's take the numbers. So what I'm going to do is take this and I'm going to run it in MATLAB. And I get my alpha value and my omega naught value. And boy, they're awfully close to each other, but they're not equal. So what happens in this case? Omega naught's a little bit less than alpha.
So that's overdamped.
It's overdamped, right? So this guy is overdamped because alpha is a little bit greater than omega naught, okay? So what does that mean if I have overdamped? The roots of this characteristic equation, how do they appear? What's the defining characteristic of overdamped in terms of those roots?
S equal to negative alpha.
Well, give me more succinct, I guess. What can we say about them? Are they real? Are they complex? Are they?
Real.
It'd be imaginary. It'd be complex.
Real.
You got two choices. They're purely real. This is the case where they're real and distinct. And what do I mean by distinct?
Unique.
They're different. Yeah, they're unique, right? They're two different values, right? So if I go back to my formula sheets there, I've got basically S1 is going to be negative alpha, and I don't know how I have it specifically set up here. I guess the way that I defined it, right, is I wrote in my roots here, S1 is, in this case, minus alpha minus the square root of alpha squared minus omega naught squared. I guess in general, what I'll say is that the S values are S minus alpha plus minus the square root of alpha squared minus omega squared. Omega naught squared, sorry. Okay. And in this case, I've written them both in there. Okay. All right. So one thing to bear in mind too, I've seen some questions going out into if you will never have a need to use any kind of an expression in MATLAB that does not exist in code that I've shown you. If it's something that I've never shown you, there's no reason you should be using it unless you want to, right? But there's no reason you should be using it. I see people doing all kinds of crazy stuff. You should only be using sort of stuff almost exactly like what I have. If you're doing it, any other commands outside of that should be completely unnecessary. Okay. Sort of a side point, but at this point, I can go in and calculate what these values are. So I calculate those values, and I do want to get what those roots are. So what are they? This -3 and -2. All right. So S1 is -3 and S2 is -2. And I want to be careful. Which one is S1 and which one is S2? I want to be really careful about that. S1 is -3 and S2 is -2. Okay. So those are my roots. So that means that what I look like here, my final value is the capacitor voltage is whatever my steady state value is, right? What we called in differential equations, the particular value, right? Plus A1. All right, it's overdamped. What's the form of the solution if it's overdamped? A1 times what?
It's A1 times e to the S1t.
Yep.
Plus A2 e to the S2t.
Yep.
Plus x infinity. Oh, you already have.
Yeah, plus that. Yeah, so that's my full solution. So at this point, right, steps 3 and 4, I need to find V infinity. I need to find V of 0, and I need to find dV dt of 0 plus. These guys help me get to my A1 and A2 values. All right, and this guy I just need because he's part of the solution. Okay. All right, so we're going to go through that. So our step 3 is to say, find the steady state values. I say for the inductor current and the capacitor voltage. I really just need it in this case for the capacitor voltage, but I want to do it for both of them. Okay. So, all right, so there's my circuit here. All right. So what do I do in this case? I'm trying to find the final value. Okay. So I'm trying to find the final value of the capacitor voltage. What are the assumptions I make here?
It's in steady state.
It's in steady state. So what do I know about my capacitors and inductors in a steady state situation?
Capacitor acts like an open circuit.
Capacitor acts like an open and inductor acts like a short, right? So I've got 12 volts. I got R1 and the inductor's a short. What about the switch here? What do I do with it?
It's a branch, it flips, so
Branch.
It's what?
it becomes
Short circuit.
Yeah, it's a short, right? Because this is V infinity. This is step 3. Step 3 is where I'm trying to find V of infinity. So that means the switch is closed. And then there's my inductor, or sorry, my capacitor. So here's V of infinity. And here's the inductor current in steady state. Okay? So what's V infinity?
V infinity is
Just do a voltage divider.
Standard curve.
Divider.
Yep, it's a voltage divider, right? So R2 over R1 plus R2 times 12 volts. And what's I of infinity here? What's the steady state value of that current?
0.
No?
No.
It would be 0 if it was an open circuit.
buddy?
So,
12 over other one.
yep, yeah. So remember, it's the inductor current. The capacitor current, yeah, if I talked about what's the steady state value of the capacitor current, that would be 0. But the inductor current, I of infinity, would be 12 divided by R1 plus R2. All right, and if you're not talking, if you want to mute yourself. All right. All right. So how do I do that here, right? So if you look at what I did in my MATLAB, right? So if you look at V infinity, right? I basically just plopped in that equation right there. I can run that. And I get 4. All right, I'm going to have to do a mass mute. How do I do that again? Somewhere in participants, right?
I sent him a message. I don't know if he'll get it or not.
There we go.
All right. Okay, so I took this value right here, V infinity, plopped it in here with the values I defined, and it tells me the final value is 4 volts. Okay. All right, 4 volts. Okay. Questions about that? Okay. All right. Step 4 time. All right. Step 4, basically analyze the circuit at t equals 0 minus. All right. Now the key thing about the t equals 0 minus is if I move the circuit over here again. So this is step 4. At 0 minus, what's true about that switch?
It's not flipped, so that R2 goes out the window.
It's not flipped. Okay, so at t equals 0 minus, it's the switch is not flipped, but our assumption here is that the circuit is in steady state.
Mm-hmm.
In other words, that switch has been in that position for a long time. So if that's the case, and again, this is my R1, this is my R2. What do I do with my capacitor and inductor?
Short and open.
Short it and open. So which one do I short?
The inductor.
Inductor. All right. Inductors are short, but what do I do with this branch with R2 here?
It's an open circuit too.
It's an open circuit, right? So I can draw R2 and just put a little open right there. I wanted to. And then there is where the capacitor would be. So this is V0 minus, and this would be I0 minus right there. Okay. So what is I of 0 minus, and what is V of 0 minus?
Is I0 minus in this case 0 because it's an open?
Sure it is. Right. There's nowhere for current to flow in that circuit. Right. Nowhere for current to flow. I don't have a path where charges could leave that 12 volt source and come back to it. Not possible in this case. Okay. What about V0 minus?
12.
Just 12.
Just 12. Okay. Because basically just by a KVL, right? If there's no current flowing, there's no voltage drop across that resistor, right? So I got to have 12 volts. Now, what does that mean about right after the switch moves? So I of 0 plus and V of 0 plus. What does that mean about those things?
They're equal.
They're equal.
They're equal.
Yep. Right. And so I guess sometimes I'll just say this is V of 0 and I of 0. Right. So I've got my initial conditions. Right. But again, this is a second order differential equation. We have two unknowns. Right. So we always need two initial conditions. Right. So I go to my step 5.
What's the difference? Sorry for interrupting you, but what's the difference between 0 plus and 0? Or are they the same thing?
So 0 is tough to say. If the switch closes at 0, right? What state am I in? Am I in a switch open or a switch closed?
Switch closed?
I don't know. I'm in the moment when the switch moves, and we're all no switch moves in 0 time, right? So the reason we define this 0 minus and 0 plus is we say, well, right at 0 in mathematical terms, that's kind of an undefined point in time, right? That's the time when the switch is making its move. So what I look at is basically right before the switch moves and right after the switch is finished moving.
Uh-huh.
Does that make sense?
Yeah.
Okay. So basically the circuit looks different at those two instants, right? At 0 minus, the circuit looked like
just a big open circuit with no current flowing through it.
Yeah, this was the 0 minus condition. The 0 plus condition is a different one. At the 0 plus condition, the switch has moved, but the problem I have, it's not a problem per se, but the issue is that the current in the inductor is constrained. It's fixed at that value, and the voltage on the capacitor is fixed at that value. And we saw that. If you go back to the sort of the lecture from last Wednesday, I looked at some examples like this. I looked at a simulation. For a short enough period of time, the inductor current is always the same. And for a short enough period of time, the capacitor voltage is always the same. Over time, the capacitor voltage, does this or something like that. But it's always smooth. So if I looked at a short enough period of time, it's effectively equal to each other. Does that make sense?
It does. It just like, I don't know. I know 0 minus is in steady state. 0 plus is in
0
our
plus
transient.
is not 0 plus is transient, and it's the
Transient.
very beginning of the transient period. It's not the
So-
whole transient period. It's a nanosecond after or picosecond after the transient period has started.
Okay. I get it.
It is just less than the 1, but actually the consider is the plus 0.
It's just right after the switch moves, right?
Mm.
And how soon that is tough to define. It depends on the values in the circuit, but it's suffice it to say it's very, very short after the switch has actually moved. And what you're saying is for that short period of time, the inductor current is pinned at a value and the capacitor voltage is pinned at a value. So what we have to do is we have to say, all right, well, if that's the case, here on step 5, what do I do with the inductor at that time?
You make it into a current source?
I make it into a current source. Now, in this case, that current source is a 0 amp current source.
Is this what happens at t equals 0, or is this our transient state?
This is what happens at t equals 0 plus.
Okay.
Right after the switch is closed. So that time period is right after the switch closes. It's the very, 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 very beginning of the transient period.
Okay.
All right. T equals 0 minus is a steady state condition. So if I had to think of it time-wise, I guess, right? If I looked at the timeline, here's t equal to 0. So 0 plus would be like right there. 0 minus is right here. Right before and right after. This is a steady state case. Right? And this is a transient.
Mm-hmm.
Because the circuit just went through a wild change. I mean, you just physically changed the way that circuit is built at t equal to 0.
Okay. It's kind of hard to visualize. Like we know like specific circuit behaviors for steady state, and we know specific circuit behaviors for transient, but at t equal to 0, like how would it be different to do a circuit analysis on the same circuit from t equal to 0 to t equals 0 plus? I guess that's my main question.
At t equals 0 minus, it's a physically different circuit than it is at 0 plus. At 0 minus, that switch is open. At 0 plus, the switch is closed. It's a physically different circuit.
I understand that, but
And over that time period, even though it's a physically different circuit, what you're saying is in those circuits, these currents have to be equal. The inductor current has to be equal and the capacitor voltage has to be equal.
okay.
No matter what, those have to be equal. Now they only over a really short period of time, they're going to start changing again. All right. So we'll let me let's just.
I don't want to.
Well, it's an important point, right? So essentially, this is me changing the switch in that circuit, right? And so right before the switch moves, the capacitor voltage was at 12 volts. The inductor current was at 0. But right after that, for a really short period of time, so if I zoomed in, I'm going to have to go. If I zoomed in right here, or right here, for like 1 picosecond before and after, a really short period of time, that capacitor voltage is going to be the same. And for a really short period of time in here, that inductor current is going to be the same. For a short enough period of time, if I zoomed in, if I kept zooming and zooming, you would see that that capacitor voltage is the same and the inductor current is the same. Now, it's going to change eventually. So this is my full transient period, probably from here to there, right? This would be my full transient period. But for a short time during that transient period, I can think of that current and that voltage being the same.
Okay.
And we need that's a physical constraint that's basically implied by the physics of the situation. All right. So, all right, back to the circuit idea here. So essentially the inductor current's constrained, the capacitor voltage is constrained. So we make those replacements. So I replace the inductor with a current source. I make sure that when I draw the circuit, the switch is closed. Okay. Now, what do I do about the capacitor here?
Power source.
Voltage source. Okay. So this is V of 0. All right. And I think that is specifically 12 volts. Okay. All right. So then the question is, all right, that 0 amps, I can effectively, 0 amps means I have an open, right? There's an open circuit there. In other words, no current can flow through that if there is 0 amps flowing. So this is VL 0 plus.
Is that going to be this case for every time we make the inductor?
Nope.
So how did we determine it was 0 amps?
Because we already did that. We did that from the 0 minus case.
Yep. Okay.
All right. So how do I go through this guy and figure out what to do here?
Do you use superposition?
I could. Yeah, it's very, a couple of different ways of doing this, right? First of all, let's say what would be in this particular case VL of 0 plus? What would that guy be? I don't need to do anything fancy for that one. How much current is flowing in this resistor right here, R1?
0.
0. So I know that it's going to be the voltage of the plus terminal minus the voltage of the negative terminal. So I know it's going to be 12 here and 12 here as well. It's going to be 0. Okay. Now, the current in the capacitor, on the other hand, what's that going to be?
The VC divided by R2
With the negative sign.
is the negative side.
Right? Negative V of 0 divided by R2. Why a negative sign? It's going the opposite direction of what the current. Sorry. Yeah, because a passive sign, right? It's going the opposite direction. It's going against that arrow that's been defined. So that means that current's negative, which means that the capacitor is starting to discharge. which if you think about it, it kind of makes sense that the capacitor is going to start to discharge because it's starting at 12 volts and it's going to, we found that the final value is 4 volts. So it is going to start to discharge, which means current's leaving it. Okay.
Do you redraw it as a open circuit because your current source was 0 amps?
That's right. Yeah. In fact, I can leave it that way. Right. So here's 0 amps. And here's R2. Right. Solid connection. Right. So a 0 amp current source is an open circuit. Right. In other words, it's saying that this current source is forcing 0 current to flow through there. That's an open circuit. All right.
Someone's buzzing.
Yeah. All right. At this point, so I'm not quite fully done with my step 5. What I have now is I have VL of 0 plus, and I have IC of 0 plus. Okay. I needed to use these to find the derivative, right? So what we said is VL over L, IC over C. This is DVC dt of 0 plus. And this guy is DIL by dt of 0 plus. All right. And in that summary that I created that I was showing you earlier, I put in that steps. I move the switches, replace the inductors, replace the voltage, the capacitor's voltage sources, find these values, and then solve for these values. Right. So there's the steps basically. All right, that you need to take for that. All right. So in my Matlab code, all right, Matlab code, I basically, put in, okay, what my initial conditions were. I put in the expressions that I just derived right there. And then I put in, okay, here's how I solve for the derivative on the voltage and the derivative on the current. And I've got everything I need for step 5. Okay. Now I get to step 6. What's the last step? What is step 6? Anybody?
Finding the unknowns.
Yeah, finding the unknowns, right? And so what we had was that V of t is V of infinity plus A1 e to the S1t plus A2 e to the S2t. Now at this point, we know V of infinity, we know S1, we know S2. What we don't know is A1 and we don't know A2. All right, so what we do is we say, okay, well, V of 0 is equal to V of infinity. And if I plug in t equal to 0 into both of those exponentials, what's that become?
1.
Right, so this,
So both the ones, so just A1 plus A2.
A1 plus A2, yeah. And then we use dV by dt of 0 plus, right? That's going to become, if I go through the math, S1 A1 plus S2 A2. All right, and that's summarized in my notes, right? So what do I do with this? I take that result and I basically say I can do V of 0 minus V of infinity equals A1 plus A2. And I have dV dt of 0 plus equals S1 A1 plus S2 A2. All right. So the way that I defined this is I put this in matrix form and I called the matrix Y equals C times A like that. And I said the first row of this guy, V of 0 minus V of infinity. All right, let's do it sort of row by row. V of 0 minus V of infinity. Then how do I enter that top equation?
1, 1.
Yep, 1, 1. And then A1, A2 here, right? So 1 times A1 plus 1 times A2. And then what do I put in the bottom row?
dv of 0 dt.
Yep.
And then for the coefficient, be S1, S2.
Yeah, great. Like that. Okay. That's so this is my C, this is my Y, this is my A. And I say A equals C inverse times Y. There's all sorts of ways to do that. All right. What I did was I gave you code. I already uploaded this code, right? Where I entered, if you look at what I did here, and let's be careful. This is where your matrix dimension problem comes in, right? So for this guy here, the Y matrix, I put my first row. So this is the V of 0 minus V of infinity, and then I do a semicolon. That semicolon puts a new row in there. Okay. And then I do the same thing. 1, 1 is the first row. Then I put a semicolon, S1, S2. Okay. And then I basically did inverse C times Y to get my A values. Okay. All right. Then basically what I do, and again, I've got the formulas for all of these, you know, in that summary. It was in the notes, but I also put it in this summary here. Right. If you go through the summary, the forms for each one are here. Okay. I'm using this form of it in this particular case. And I have, sorry, too many things open. All right. Actually, I wanted to go to my Matlab. All right. I use the form for the overdamped. Okay. So A of 1, we said, is the first value in here. A of 2 is the second value in here. And I enter that and go ahead and plot it. All right. So if I run this whole thing, let that run. Takes it a second to make the plot. That's what takes the time here.
I'm not understanding this matrix too well.
You're not understanding how it was created?
Not really. So V0
Okay. Well,
minus,
I mean, and if you, let me put it this way. If you don't understand how it was created, that's okay. Do it whatever way you want. You're not obligated to use this approach. I'm saying this, I find this to be the easiest approach. But what you have here is 2 equations and 2 unknowns, right? This side, everything on this side here is known. S1 and S2 are known. A1 and A2 are the things you don't know. Solve that whatever way you want. You don't have to do it that way. I'm showing you how I would do it. But do it whatever way you want to do it.
can I see the MATLAB code one more time? Because I just clicked I just saw the matrix now. I understand where you're coming from. But
Well, yeah, so, you know, the code is here. You can take a closer look at it. This code is posted as well. If you look on Canvas, you'll see this code. If I look at the plot that's produced, right, the plot for the capacitor voltage makes sense. Starts at 12, goes to 4, because we said the initial value on the capacitor was 12. We said the final value on the capacitor was 4.
so why are you how is A the inverse of C times Y? Like what's the logic?
That's just linear algebra, right?
Okay.
If I wanted to solve for an unknown, all right, if you've taken linear algebra, you should have seen how to do that, how to compute an inverse matrix.
Basically dividing Y by C.
That's right. Yeah, you're basically
Yeah,
trying to perform division. But again, if you're not comfortable with that, I mean, you know, you've known how to solve 2 equations and 2 unknowns since high school, right? You know, you could certainly do that the long way if you wanted to solve, you know, plug one equation into the other and then go that way.
Okay.
If you have taken linear algebra, there's all sorts of other ways you could do that. All right. All right. That's enough second order for a lifetime. All right. Like I said, I'll post 2 more examples online, but I'm done with that for now. All right. So second order circuits, they're important. They happen a lot, and they happen a lot in digital cases, right? But it's not sort of everything that we concern ourselves with. All right. 2112 is much more about what I would consider to be AC circuits, which really typically means that I'm talking about sine waves. So let me go and start that discussion. All right. After spring break, we're going to have a lot to say about how we deal with AC circuits, but I wanted to introduce that concept here now. All right. So let me, DC versus AC. All right. So you guys know what is DC, what is AC? What are the terms?
Direct current and alternating current.
Direct current and alternating current. All right. So that doesn't really make anything any more clear. What is the difference between a DC waveform and an AC waveform?
Direct,
DC
I
is
think current
constant.
goes only one way. In direct current and alternating current, like the current can kind of go back and forth.
Yeah, that's sort of correct. Yeah. So
Well, one's constant and one's not, right?
yeah, that's right. And that leads to the fact that the current can go both directions in AC. But yeah, so the way I would say is this guy is constant versus time. Boy, that doesn't look like the word constant. And this is time varying. Okay. Now, what that means is in DC, if I looked at what a DC waveform looks like versus time, it would look like that, right? Give me an example of a source that would be constant.
Regular battery, AAA.
Yeah, AAA battery. A AAA battery, you know, sometimes I draw it like this. That guy would be 1.5 volts, all right? If I had a AAA battery, right? It would be that value, and it should stay that way for as long as the battery lasts, right? Once the battery starts to die, the voltage will drop a little bit, but essentially it looks like that. Now, AC means it changes as a function of time. All right, that means it could be something like this. All right, the time. What would you call that waveform? Anybody have a name for that?
The square wave?
That's a square wave. Okay, and that's a pretty common type of waveform. And then the other one that's pretty common that we deal with, and there's many you could talk about, but the other common one would be the sine. And we use sine and cosine kind of interchangeably, right? Cosine, you know, is different than sine, obviously, but oftentimes we're going to say AC waveforms are sinusoidal. One of the things that you learn in 2254 is that, and you may have seen this in other places, any AC waveform, and let me ask this, somebody who's, so Anthony, are you there? Any AC waveform, maybe Anthony can answer this one. What is any AC waveform made up of? I'm putting you on the spot.
What's an AC waveform made of?
Any AC waveform can be the sum of sines and cosines. Okay. And that's a theorem called basically the Fourier theorem that you'll learn about in 2254 and 3111. But any AC waveform can be made up of sines and cosines. Okay. So sines and cosines have a really special place. And these guys are really where we start our analysis of AC circuits. Okay. And they're common. All right. So here's you know, an example. So they're common all over the place. So power is one place. I'll give you a couple of examples. So power is one, and then there's others that we'll see here in a second. But in the case of power, this is an example I gave. So a photovoltaic array. This is solar, right? So the type of circuit you deal with is an inverter. It goes from DC and converts it to AC. Okay. So in this particular case, if you look at this guy, and that's not quite constant, but that's sort of DC, right? That yellow waveform is the voltage across that at the output of that PV array. And it's got a capacitor there in parallel with it, but it's noisy. In other words, I see some spikes here, but it's pretty much DC. Okay. The green waveform in both the picture on the left and the picture on the right, that's the grid voltage, right? That's the voltage that Duke Energy provides over there, okay? And that, sure enough, looks like a sine wave, right? Now, I also included this yellow waveform over here, which is the output voltage of this, it's this device. I called an inverter, which if I look at it, if you really zoomed in on this guy, you'd see this guy here is a super fast square wave, right? Which is ultimately an AC waveform, okay? So what we can see is, you know, in power, for instance, you know, sinusoidal voltages, the grid is a sinusoidal voltage, okay? And we'll talk more about power, you know, later on in the semester, but in that case, I'm talking about a cosine or a sine of voltage that I get. In other words, if I put an oscilloscope into a wall outlet, I would see a waveform that would be sinusoidal. Anybody know what the frequency of that waveform would be?
60 hertz.
Yeah, 60 hertz. Okay, at least in the US. If I was in Europe or somewhere else, maybe it'd be 50 hertz, but here it's 60 hertz, right? All right, so we'll talk more about that in a second here. So power, it's common, but radio would be another place, okay? So let's say you're listening to, you know, I don't know, let's say you listen to, I don't know, anybody actually still listen to the radio? Give me a radio station.
95.1.
98.5.
102
All right, well, there's a lot of them. All right, now I'll go with the 98.5. Which one did I choose? What kind of music did I choose?
That's a country station.
It's a country station. All right.
Oh man.
Y'all hating on country. Y'all need to get out of here.
All right, so we got 98.5 megahertz, right? So that tells me that is a sine wave, all right, that has a particular frequency, all right? And it looks like this guy up here. And when they send radio signals, if they send an AM wave, what they do is they change the amplitude of it. If it's an FM wave, they change the frequency of it. So it has this sort of weird sort of accordion effect. But clearly, those are sine waves, right? So that's pretty common for us to utilize that. And then audio is another case, right? So if I was looking at an audio waveform versus time, so this would be a voltage here. All right, versus time. What I would see is something that looks like that. And in fact, I guess what I can do here is I'll turn I'll the camera on here per se. All right, so if you see, I don't know, can you guys actually see the phone there?
Yeah.
Yes, we can.
All right, so as I talk into the microphone here, it's picking up my voice. And as it picks up my voice, what you see is oh, I guess it's turned that way. What you see is, so that the time axis is here, right? And the voltage axis is up and down, right? So as I speak, what you see is essentially a sum of sine waves, right? Which is basically made up of the different frequencies that are there present in my voice. And there's tools, like for instance, I've got another tool I can do here. All right. There's a tool like this guy here, which can tell me what frequencies are actually present in my voice. All right. That's another tool you learn about later, right? But I can actually see what sine waves are there using some other tools. All right. Key thing is, bottom line to all of this is sine waves are really important in a lot of practical problems, right? So audio signals, like we said, right? Audio signals are a sum of sine waves. So if I have a CD or an MP3 file or whatever the case may be, right? Inside those things, I am going to have sinusoidal waveforms. Power system has sinusoidal waveforms. Radio has sinusoidal waveforms. The frequencies might be different, right? But I certainly have situations where I have lots and lots of sinusoids. Okay. All right. So that means that we need to define some things about the sine function. All right. So in general, the sine function is a function of angle. Okay. So I wrote out here. All right. So if I have a sine function, it starts at 0, goes to 2 pi. All right. And I make some definitions here. What do I call this guy here? X sub m. What is the term that I use?
Amplitude.
The amplitude. Right? The amplitude is the peak value. This guy is the amplitude. By default, what's the amplitude of sine of theta?
-1 to 1, 1.
Yeah.
-1.
Yeah, this guy is always between -1 and 1 by default, okay? If I say that it's 5 times sine of theta, that means it goes between -5 and 5, okay? And by default, by definition, I don't give a crap what TI says in your calculator. By definition, sine is periodic in 2 pi radians, meaning it repeats after 2 pi radians. So if you use the sine function, by definition, it goes from 0 to 2 pi. All right. Now, you can change your calculator and force it to be 360 degrees. Okay. But it is by definition in radians. Now, one of the things that we're going to see here is when we deal with stuff in the context of, you know, these ECE problems, we always talk about functions of time. And I think this is really important, right? Sine is defined in terms of angle, but we talk about voltages and currents as a function of time, right? Because what I do is I build a circuit and I measure the voltages and the currents in that circuit. They fluctuate as time advances. So we say that they are functions of time, which means that the angle is changing over time. And the way we write that is we say that that angle varies with an angular frequency omega, and as time advances, the angle advances. All right. And so we have a couple of important definitions that we give here, right? So omega, we say, is the angular frequency of this guy, the rate at which the frequency changes in radians per second. Okay. And the sine wave is periodic in 2 pi radians. And so what that means is when omega t equals 2 pi, that's the time at which I have finished one period. Okay. Now, the time that it takes to finish one period, we give a name, the period, which we call t. Okay. We call that t. So if I'm looking at this formula here, omega t equals 2 pi, right? That happens at time big T, right? So I see that omega is always 2 pi over the period, okay? T is the period, omega is the rate at which that frequency or at which that angle advances as time moves, okay? So we define a couple of important things here. All right, the other thing that we talk about the angular frequency, the period, the amplitude, and then we also talk about the frequency in hertz or units of seconds. All right, by definition, the period and the frequency are one. So the period is 1 over the frequency. Okay. So let me ask you this. So I said the power system has a frequency of 60 hertz. All right, that means F is 60 hertz. So what does that mean? How many periods does that guy have in 1 second?
1 over 60.
That's the length of one period, 1 over 60. How many periods does he have in 1 second?
60.
60. All right, so the period is 1 over F. All right, the period is 1 over 60, which is a bad number. It's like 16.667 seconds. Okay. And so there's 60 periods in 1 second. So in other words, 60 cycles per second. Sometimes the way people say that, right? If I asked you, well, what's the angular frequency of that? What would that be?
2 pi.
Just 120 pi.
Yeah, 2 pi. 120
yeah.
pi. And that would work out to be about 377 if you calculated that. Now, and that's radians per second. Now, a couple of things. You will never hear a real engineer use omega, okay? It is required per the definition of the sine function but you will always hear real engineers talk in terms of hertz, right? They'll say it's a kilohertz or 60 hertz or it's 480 hertz or whatever. You'll never hear omega. Similarly, when we start talking about angles, they'll never refer to angles in radians. They will always refer to angles in degrees. And so I will use degrees and I will use hertz most of the time. All right. That's kind of important to remember. All right. As we go through this. Okay. All right. So a lot of this stuff is basic stuff that you guys should have had some understanding of prior to this from physics. And you should, if you haven't seen it yet, you'll certainly be seeing it in 2254 if you're in that class this semester. All right. So a couple of things. When I want to look at the picture of this, I think of any sine wave as having kind of three important parameters. If I wanted to, so let me ask this question, right? So if I wanted to express and draw a sine wave, I would need to know three things. That's what I've got here. I would need to know its amplitude. I would need to know its frequency. And I need to know its offset. All right. So oftentimes in circuits, what we do is we kind of think of cosine as the sort of what I'm going to call the basis, right? So in other words, the cosine function is sort of, we define everything relative to cosine. In other words, we talk about how much shift or phi we have and what the amplitude of it is. Now I'm going to call that guy phi phase shift. So we talk about this offset. We talk about the frequency, which tells us how fast it varies. And we talk about the amplitude, which tells us how big it is. Okay. So, all right. The waveform that I've got drawn here, let me see. I want to skip ahead here. I think I got a blank slide here for a second. All right. So if I drew cosine, what would cosine look like versus time? So in other words, I'm going to draw cosine omega t. What would that look like?
Just the peak of it, it starts at 0.
Yeah, the peak of it starts at 0 and goes like that. Right.
Oh, the mic is unmuted.
Yeah. All right. So let's say, what's the height of this guy? Cosine omega
Be 1.
Yeah, from 1 to -1. So let's say, I said 2 cosine omega t. What would the height there be?
2.
Yeah, 2 and -2. Now let's say I wanted to draw 2 cosine omega t plus 45 degrees. What would that look like?
You're going to shift your wave 45 degrees to the left.
Shift it 45 degrees to the left. Okay, so has Yabu started talking about this in 2254?
Yes. A little bit.
Yeah, a little bit.
A little bit. All right. So I don't know exactly what 45 degrees it's going to go.
Not in like angle measurements though.
Yeah. All right. But it's gonna look like that. All right. In other words, the way I think about this is it's pulled to the left because the peak that would have otherwise happened at 0 got pulled earlier in time. Right. So by saying plus 45, it got pushed earlier in time. If it had been minus 45, it would have gotten pushed to a later point in time. All right. But the critical thing is what it says is if I told you the amplitude, which I called XM, I told you omega, and I told you this offset here, 45 degrees, you could tell me the value of that waveform at any point in time, right? If I gave you a T, you could tell me the value. So this is kind of, in some way, if I know just these values, it's like compression, right? Think about like if I compress a file, right? You make that file smaller. You basically say, I don't need to know every little detail in that file. I could just know a couple of key things. And then from those key things, I could regenerate everything. Okay. So the frequency, the amplitude, and the phase are really important to me because what we're going to find out is that in a given circuit, if I put in a voltage source, let's say that has a particular frequency, the only thing that circuit can do is to affect the amplitude of that voltage and the phase shift of that voltage. It can't change anything else. It's not going to, you can't put a cosine in and get a square wave out or something like that, all right? If I put a cosine in, I'm going to get a cosine out with a different amplitude and a different phase, all right? So a couple of things. This offset value, I've used this term a couple of times here. This offset value here is sometimes called the phase shift, all right? And we measure that in radians or degrees. And you will almost always, I think exclusively probably from me, hear me refer to that in degrees. Because like I said, engineers really never use radians. You'll never talk to a guy at Duke who says, well, the voltage at that bus has an angle of pi/4, right? They're not going to say that, all right? They'll put it in degrees, okay? All right, so there's a lot to talk about here, but you know, fundamentally, if I had a circuit that had all resistors, right? So here's a case where I basically built a circuit. A little tricky maybe to follow exactly how I've set this up. But what this guy is I've got a voltage source and 2 resistors like that. If I told you I had a voltage source like that with here's R1 and here's R2, and I wanted to measure the voltage across this R2, what is that circuit? What would you call that?
Voltage divider?
Voltage divider.
It's a voltage divider, right? And so you would expect that the voltage across that R2 would be smaller than the voltage coming in, right? And that is, in fact, what will happen, right? If the blue is the input voltage here with a 10-volt source, the red is the output voltage, right? So it's a smaller voltage. So if I look at it, it's, you know, if I have purely resistive circuits, all the analysis that I need to do is everything that I've done before. The problem I run into, and what we're going to pick up with next time, is what happens when I have a capacitor or an inductor, right? If that's the case, what should happen if I have an RC circuit and I have a sinusoidal source? What always happens? Well, I have a differential equation. If I have a differential equation, I always have 2 parts to the solution to that differential equation, right? What are the 2 parts in general to any differential equation?
Homogeneous in particular.
Homogeneous in particular, right? The particular is what I call the steady state, and the homogeneous is what I call the transient response. So there's going to be a transient response and there's going to be a steady state response. What's that particular or steady state response going to look like? From differential equations, you should know what's it going to look like. If I have a cosine as my source, I'm still going to have cosine as my steady state response. All right, so we're going to see this, right? Basically, what I'm going to get is some transient response plus some steady state response. And what we're going to say is we already know how to do the transient response. What does the transient response of any differential equation look like? What's always in a in the transient response of a differential equation? What type of function?
Exponential.
Exponential, right? And that exponential always does what if I wait long enough?
Go to zero,
Goes to zero.
after
It goes
5
to zero.
tau.
It goes to zero after it dies out, and I'm left with essentially a sine wave. All right. And so what we're going to do is when we go into AC circuits, we're not going to worry so much about the transients. We're going to worry more about what happens in steady state. All right. Now, if you look at the steady state, which is out here, once the transient's dead, what's the difference here? If you look at when I had a purely resistive circuit, and I'm going to wrap up here in a minute. This is the input voltage. This is the output voltage. Look at that relationship versus the input and output voltage once I have a capacitor. So here's the peak value of the voltage of the input. Here's the voltage at the output. What looks different in this case?
It's
not that much
amplitude is less
different.
and shifted.
It's shifted, right? The amplitude's different, but it's shifted. That shift happened because of the capacitor. All right, so basically what we're going to see in AC circuits is we can actually simplify it and get rid of the differential equations because there's some rules of thumb that we can follow associated with what that phase and what that amplitude change does. And that's what we're going to pick up with after spring break, is to try to understand AC circuits and the way in which we sort of take all of our knowledge from circuits 1 and expand it to include what resistors and capacitors do, in particular when I'm dealing with steady state AC circuits. Okay. So that is all I've got for today.